All around us, there's this invisible world of power. It's humming in our walls, it's flowing under our streets, but how does it all actually work? Well, today we're going to decode the secret language of electricity, all the way from the power plant right to your phone charger.
I mean, really think about it. We plug things in every single day without a second thought. But behind that one simple outlet is a massive, incredibly complex system that stretches for hundreds, even thousands of miles. Getting power to your phone isn't magic, it's a language, and it's written with absolute precision.
And this is its dictionary, the electrical plan, or what we call a blueprint. This is the master code that tells electricians exactly where every single wire, every switch, and every outlet needs to go to bring a building to life.
But before we zoom in on just one building, we've got to pull back, way back. We need to understand the epic journey electricity takes to get there in the first place. Your outlet is just the final stop on a trip that starts on a massive, continent-spanning network we call the grid. So you might be wondering, why does the grid use such incredibly high voltage? It sounds kind of dangerous, right? Well, think of it like a fire hose. If you want to move a huge amount of water over a very long distance, you need intense pressure. It's the exact same idea for electricity. High voltage is like high pressure, pushing all that power across the country with as little energy loss to heat as possible.
Okay, so the power has made its cross-country trip. Now what? How does it get from those gigantic towers down to your street and finally into your home? This is where the design of the local network becomes absolutely critical. Turns out, local grids basically come in two main flavors. First, you have the radial grid, which is common in rural areas. Think of it like a tree. It's simple, it's cheap to build, but if one branch breaks, everyone downstream loses power. That's why cities use a mesh grid. It's more like a spider web. If one connection fails, power just finds another way to get to you. It's more expensive, for sure, but for a city, that kind of reliability is non-negotiable. So, now we're finally at the building, and this is where we get to learn a specific dialect of this electrical language, the blueprint itself. This is the electrician's detailed roadmap for turning a complex plan into a perfectly functioning electrical system. Every single blueprint is going to start with a title block, usually down in the bottom right corner. Think of it as your You Are Here map. It gives you all the crucial info, like the project number, the date, the scale, and exactly what part of the building this plan is covering. But okay, what about all these crazy-looking symbols everywhere? How do you make sense of them? That's where the legend comes in. Seriously, this is the Rosetta Stone of the whole operation. It translates every single symbol into a real-world object, from a simple outlet to a complex light fixture. It's the key to speaking the language. All right, you ready? Let's actually put these new language skills to the test. We're going to look at a few symbols in the legend and then go find them on the real plan. This is where it all starts to click. Let's start with something we all know. A standard electrical outlet. Over in the legend, you can see its symbol, a little circle with two parallel lines. Now, look over at the plan on the right, and boom, there it is. That simple symbol tells the electrician exactly where to install an outlet. Okay, let's do another one. How about a light switch? The legend shows us the symbol, which kind of looks like a dollar sign, right? And on the blueprint, yep, we find it right next to the doorway, exactly where you'd want it to be. This shows how the plan dictates not just what gets installed, but the precise where. And for our last one, let's find the real heart of the system, the electrical panel. The legend gives us its symbol, this shaded rectangle, and on the plan, we can see it's located in the mechanical room. Literally every single circuit in this area starts right from this spot. But, these plans aren't just about where to plug in your lamp. A huge part of this language is all about safety. It's about creating this whole network of silent guardians that are there to protect people and property. Just take this exit sign. I mean, we see them everywhere, right? But have you ever really thought about how they stay lit when the power goes out? It's a perfect example of a life-saving safety system that's designed right into the blueprint. It's actually a brilliantly simple system. See, normally, the sign is just running on the standard AC power from the wall. But at the same time, it's also charging up an internal DC battery. So if that main AC power ever cuts out, an automatic switch just instantly flips over to the battery. The light doesn't even flicker. It's a perfect little failsafe. And back inside that main panel, you've got the ultimate guardians, fuses and circuit breakers. Their one and only job is to sense a dangerous power surge and instantly kill the circuit, stopping a potential fire before it can even start.
Without these guys, a faulty toaster could turn into a total disaster. They are the true unsung heroes of electrical safety. So we've learned the language, we've decoded the symbols, and we've seen the safety systems. There's just one last piece of the puzzle. How do you turn these little drawings on a piece of paper into a full-sized, real-world building? Well, it all comes down to scale. Remember that title block we talked about earlier? Well, that's where you'll find the magic conversion factor, the scale. A scale of, say, 1 to 200 tells an electrician that every single unit they measure on this drawing represents 200 of those same units out in the real world. The math itself is super simple. You just measure a distance on the plan, multiply it by whatever that scale factor is, and bam, you've got your real-world measurement. This is literally how a drawing becomes a building. Let's actually try it. See this wall on the plan? We measure it, and it's 127 millimeters. Okay, so we multiply that by our scale, which is 200, and we get 25.4 meters. And just like that, a line on a page becomes a real physical wall. That is the power of scale. You know, as the author Cornell Barbu puts it, learning this language, it's about more than just the technical stuff. It's about understanding how we can take an idea, just an idea on paper, and piece by piece build something real, something that lasts. So, the next time you flip a switch, I hope you see a little more than just light. I hope you see the vast grid stretching for miles, the detailed blueprint behind the wall, and the entire hidden language working together, all in harmony, just to power your world.